All right, good morning, everyone. I show 10 o'clock Eastern, so let's go ahead and get started with the session today. Excuse me. My name is Tom Limeculer. I'm from the Johnson Space Center in Houston, and I'll be chairing our Interdisciplinary 1 session today, along with my co-chair, Michael Elmore, from the Kennedy Space Center.
All right, well, good morning, everybody. My name is Alex Pagano. I'm here from the Aerospace Corporation, and today I'm going to be presenting some work that the Thermal Control Department did on additively manufactured heat pipes. So a quick overview of our additively manufactured heat pipe project. The goal of this project was to design, print, and assess the functionality of an additively manufactured heat pipe. The primary use case for this is to reduce unit temperatures and temperature gradients across a spacecraft while maintaining a similar production cost and schedule for the manufacturing. Our hypothesis was that 3D printing will allow for more optimized heat flow paths and fewer geometric constraints because it integrates heat acquisition, heat transport, and heat rejection components into a single fabrication. Doing so removes interface resistances and in turn can reduce temperature gradients across a spacecraft. The experiments in this work were conducted by comparing the temperature drop across an empty heat pipe to a methanol-filled heat pipe. The goal of this was to simulate a basic spacecraft structure, like a spacecraft bus panel, and compare that to a spacecraft structure which would have additively manufactured heat pipes embedded in it. The filled heat pipe tests were then compared to a numerical heat pipe modeling tool developed using Python by the Thermal Control Department with a target of 25% correlation error set for temperature drop predictions. That was the primary metric that we were comparing to. Moving into the test fixture geometry, the additively manufactured heat pipe geometry was constrained by metal powder bed fusion printing capabilities. So a few of the issues that we ran into were overhangs. PBF printing allows for only a 35-degree overhang, and any steeper overhangs than that require excessive support material, which you can see up in the top right picture. And this is going to incur increased costs, increased likelihood of print failure, and when we're printing using metal, especially on very small resolution parts like the wick for a heat pipe, it's very difficult to remove the support material from the inside of the heat pipe. Additionally, the print orientation is very important. So a traditionally axially grooved heat pipe can only be printed in a vertical direction due to those overhangs, but this comes with now path and size constraints. So vertical prints will allow only very minor curves in the heat pipe path to be printed. Due to this, a circular cross-section with axial grooves around the entire circumference is of interest for vertical prints. Horizontal printing would give more freedom in terms of the size and the heat pipe path, but the grooves cannot be printed around the entire inner diameter of the heat pipe due to avoiding overhangs. So limitations there are that horizontal prints will allow only certain heat pipe cross sections to be printed. An example of this would be the triangular cross section you can see on the bottom right of the page, where you only have wick across the very bottom of the heat pipe. That was something that was printed in this work, but that the testing was outside of the scope of, so that remains to be tested in future work. The final requirement would be size requirements. So small features can be lost in the print resolution, and in a work like this, the wick geometry particularly is of very, very high interest there. For groove wicks, it's a bit less important, but to move into sintered or screen wicks, the print resolution becomes an increasingly important factor. Additionally, this is more on the manufacturing side, but printing any holes, small holes, whether that's for bolted connections or things of that sort, can also be lost when you're using additive manufacturing. Moving into the test article design, the initial objectives of our design were to demonstrate failure-free printing of heat pipe geometry. With that geometry, we want to obviously demonstrate heat pipe functionality, and in doing so, we want to explore a simple sealing approach. So creating a hermetic seal is one of the biggest issues that we face, and without a hermetic seal, you cannot have successful heat pipe operation. So our goal was to create a simple approach that would allow for reproducibility of results and a long time usage of our hermetic seal. We elected to use a vertical configuration in order to reduce the risk of any print failure. In doing so, we're allowed to print grooves around the entire circumference, so there was no wick overhang. You can see we have a fin section at the top for the heat rejection on the condenser, and the angle of those fins was determined by the maximum overhang able to be printed that I discussed previously. It was 35 degrees. We avoided any curved paths just for simplicity for a first design. And surprisingly, some small features like the inside of the wick and the holes at the top of the heat rejection section showed very good resolution. So we were happy with that. A SolidWorks simulation was run to confirm adequate heat rejection capability of a fan and a finned heat sink. In doing so, we then were able to run the test in air using a simple fan cooler rather than needing to run with a chilled water loop, which again aided in the simplicity of our design. The test article itself includes a flange with bolt holes to mount the test article, which were tapped post-printing, and additionally bolt holes on the fin section to attach a fan, which also were tapped post-printing. So the entire test article that you see in that top picture on the right was one piece of 3D printed aluminum. We also performed a simulation and a residual stress assessment in order to determine the success of printing. One primary concern, especially when using a vertical configuration, is we want to make sure that there's no recoater blade crash between the blade itself and the test article while it's being printed. So the analysis predicted that there would be no crash, and this was validated when we actually printed it. Additionally, there was a maximum residual stress of 307 megapascals predicted. For this material, this results in yielding but no breakage. So the process simulations predicted successful print, and the residual stress was within material allowable limits. So we went ahead with the printing. Here are a couple pictures of the prints themselves. The one on the very left side here is right after the print finished, when the prints were still on the build plate. The one in the middle was the prints after sandblasting. And then on the right here, you can see some of the dimensions of our cross section. So even at 0.014 inches in a spacing between those grooves, we were able to maintain very good resolution. There wasn't any excessive support material there. We didn't require any post-process machining whatsoever. The only post-process that we did was sandblasting. So no post-process machining was required, and no isostatic compression, any heat treatment along that sort was required either. So again, that aids in the simplicity and reduces the cost and reduces the time in the manufacturing for incorporating these into a space vehicle. Our test setup itself is depicted here on the right side. It consisted of the test article, which was bolted into a G10 base plate. The goal of this was to insulate the bottom flange and reduce any conductive losses. We used a gap pad to accommodate uneven surfaces between the heater and the flange, and also to prevent damage to the heater. This wasn't a conductively isolated gap pad. The goal of this was just geometry. It wasn't to add any insulation there. We used a Kapton heater to apply heat into the base of the flange using a constant voltage and a measured current to specify different power values. There were 8 thermocouples applied along the length of the pipe. A quick note on that was that the TC8 there at the bottom was applied after the field data was obtained. The field data that we're going to present is only going to include the first 7 thermocouples. Using these thermocouples, we measured the temperature drop across our heat pipe. That's our primary metric of comparison, is the temperature gradient. And we did that by subtracting the temperature readings between TC4 and 5, which read the same value, and TC6 and 7, which read the same value. So that corresponds to our evaporator section and our condenser section, respectively. A fan was placed on the condenser section in order to provide heat rejection and reduce the overall test temperature, since we were testing just in air. And a swage lock fitting was used to seal the pipe once it's filled. We actually threaded the fitting into the pipe after tapping that hole at the top. And then we used Tor Seal to seal the fitting into the pipe as well. The reasoning for this was that we initially started using a simple NPT plug with some Teflon tape, but unfortunately that failed to seal. We were getting leakage out of the top of the pipe, so we opted for a more permanent approach by sealing one end of the swage block permanently into the pipe. Due to the size of the swage block compared to the NPT fitting, we had to incorporate some standoffs there to offset the fan. You can see on the right side here is an actual picture of our test setup. The test procedure consisted first of placing our entire test article on the balance. we would fill it to 1 gram of methanol. So all of these tests were performed using methanol as our working fluid. The pipe itself had a maximum fill volume of about 1.2 grams. So you can see we fill it almost all the way to the top. And then in order to create a hermetic seal, we use a fill, purge, boil off method. So what we did was we powered the heater on to 10 watts. We began boiling the fluid, and the goal of this was to purge non-condensable air from within the heat pipe. So as we're boiling and the balance reading approaches our desired charge mass, we close the pipe using the swage lock fitting and attach the fan to the top of the condenser section, and then simply allow the thermocouples to reach steady state. So in most of these tests, steady state was reached after approximately an hour. After that, we would record the temperature drop, the delta T, from the evaporator, which was thermocouples 4 and 5, to the condenser, thermocouples 6 and 7. And then we would increment or decrement the heater power and repeat. All of our test results were measured at 3 input power levels, which were 5, 10, and 15 watts. And I say increment or decrement because heating versus cooling, in terms of our boiling behavior in the evaporator section, we noticed became very, very important. I'll discuss that later, but in some cases we started at 10 watts and then we would go down to 5. In others we were at 10 and we went up to 15. But in every case we somehow captured 5, 10, and 15 watts on at least heating, if not cooling as well. A quick overview of our test results. You can see the very top curve here is our dry heat pipe. So this data was obtained by powering on a heater at 5, 10, and 15 watts, and no working fluid was present in these tests. So this is to simulate a basic spacecraft structure, like a bus panel, without any embedded heat pipes. The 4 curves at the bottom, there are indeed 4. The green one and the dark purple one overlap, except for in that last 15 watt case, but the 4 curves at the bottom represent 4 filled data sets. So these are run with different charge masses that you can see in the legend, consisting of between 0.39 and 0.54 grams. And what we did was at each power level, we took an average delta T. So at 5 watts between those 4 curves, we averaged the y-axis value, the delta T value. We do the same for 10 and 15 watts. And then if you take that value, we call that delta T filled at a given heat input value. And if you take the ratio between that and your delta T dry, which is that top curve, you get the numbers in this table here. So you can see at all heat input values, we demonstrate significant improvement when we're using a filled heat pipe, but particularly at high heat inputs, 15 watts, see almost a 90% drop in the delta T. So a significant average delta T reduction seen across all 4 runs. And this validated our heat pipe performance. So we can conclude that additive manufacturing is viable, and it does create a heat pipe which can be sealed and can operate in heat pipe orientation. Moving into an overview of our Python model. The Python model is an 8-node model, which takes into account resistances through the condenser, wick, and outer wall, which are simply conductive resistances, a 2-phase condensation resistance in the condenser, a vapor pressure drop resistance, a 2-phase resistance in the evaporator, and then conductive resistances through the evaporator wick and wall as well. The primary model inputs are the heat pipe cross-sectional geometry, the working fluid properties as a function of temperature, the desired heat input value, the charge mass, and the outer wall temperature. So for primarily your 2-phase resistances, these values are temperature dependent. So in order to calculate a resistance, you need knowledge of the absolute temperature at that node as well. So because of that, we needed to enforce some temperature constraint along this node network. It could be any value, but we opted to use the condenser outer wall temperature, which we've denoted to be TW, because typically this is a function of your heat rejection, and it's a pretty well-known temperature. A quick note is that these node numberings do not correspond particularly to the thermocouple values. So you can see TC5 and TC6 are on this diagram as well. So the thermocouples and the node model do offset slightly. The basic formulation for the code is the model calculates a resistance between each node. So it starts at TW, it would calculate a conductive resistance between TW and T1, and then from knowledge of the heat input and the individually calculated resistance, we can calculate 1 delta T between each node. So moving from T1, we know the calculated resistance, can calculate a delta T between TW and T1, and then same thing, you know T1 now, calculate a conductive resistance through the wick, calculate your delta T, then you know T2, and it marches sequentially down the line there. A few of the kind of more important resistances, the vapor pressure drop resistance, or hydrostatic and viscous vapor pressure drop, is typically negligible. Normally it's modeled sort of as a short circuit. Here we include it, but we also measured that the resistance value was orders of magnitude smaller than others. The condenser resistance is modeled based on simple Nusselt film condensation theory for a thermosiphon, basically. And then the evaporator resistance is very interesting. So this corresponds to one of 3 different evaporator models. And what I mean by that is that for every solution, so for every heat input value, the code is going to march all the way to T4. Then at T4, the solution is going to split into 3 unique solutions. Where those solutions differ is they assume that a different heat transfer process is occurring for the evaporator resistance. So what I mean by that is that we will assume that either natural convection, partial nucleate boiling, or full nucleate boiling is occurring to calculate the resistance between the T4 and the T5 nodes. The reason for this is that we were noticing through our testing that the onset of nucleate boiling, which depends on a wider range of factors, including your input power and basically the temperature difference between T5 and T4, it was delayed. And because of that, with delayed boiling behavior, we wanted to be able to capture the different modes that the heat pipe could be operating in. So in doing so, again, we end up with 3 unique solutions for every heat input value. I have a flow chart. If I'm sure that that's a little bit hard to get your head around, but I can show that later if needed, and we'll also discuss some results on the next slide. But the primary outputs are the total temperature drop across the heat pipe and the total heat pipe resistance for each evaporator model and for a specified heat flow range and charge mass. Here are a couple pictures of our sample outputs. So as I said before, these correspond to 3 different solutions. So for every heat input value, in this case, the code was run for a sample geometry from 5 to 20 watts. At 5 watts, all the way through 20, there are 3 different temperature drop solutions. Again, those 3 solutions only differ in that the node network is changed slightly by changing the evaporator resistance from nucleate pool boiling to partial nucleate boiling to natural convection. So you can see nucleate pool boiling is our most efficient form of heat transfer. So it results in the lowest total resistances and the lowest temperature drop. After that is partial nucleate boiling. The term partial nucleate boiling can really refer to a process that corresponds between these red and these green curves. There isn't a discrete, typically, model for partial nucleate boiling. For the purpose of comparison to experimental data, we selected the blue curve, which is based on the Rosenau boiling correlation. But partial nucleate boiling behavior can really occur in that whole shaded region between the top and bottom curves. And then our least efficient form of heat transfer is just pure natural convection occurring along the evaporator wall due to just the temperature gradient and the working fluid being in a pool. So that results in the highest resistance and also the highest temperature drop. One thing that is important to note is that our pipe resistance actually decreases with higher heat fluxes. And the reasoning for that is that the efficiency of boiling and natural convection increases as the heat flux increases as well. An overview of the experimental results and the model comparison is shown here. Note that this does say heat input corrected, and what I mean by that is that we accounted for convective losses on any exposed sections of the heat pipe, as well as conductive losses through the G10 base plate. So for each of these tests, the heater specified value was 5, 10, and 15 watts, but you can see after accounting for heat flow losses, those values drop by a couple of watts depending on the case. But across our 4 runs, you can see the 3 curves that are presented are the code model outputs, and then the measured values are the yellow triangles and the purple diamonds. So one important thing to note, and I'll touch on this a little bit later though, is the wide range in wettability, surface roughness uncertainty due to our 3D printing, any contaminants. They can create a really wide range of partial nucleate boiling and natural convection behavior. So because of that, at similar power levels, we get very different measured heat flow values. So across these runs, the model curves remain more or less the same. They differ slightly due to different working test temperatures. Again, that TW constraint changes. But the experimental values, we do see a very wide range in the results there. How we concluded different results was we present all three of these evaporator models, and then we make an assessment about the heat transfer regime for each heat input. So we can tell just by the trend of the experimental data that as the heat input increases, you can see we get a sharp drop in the measured temperature drop, which indicates to us that at low heat input values, nucleate boiling had not been initiated. And then as that heat flux increased, gradually we initiated boiling. So we shift from a natural convection model to a partial nucleate boiling model to, at high heat fluxes, typically a full nucleate boiling model. Then for each heat input value, we can make a conclusion about the heat transfer regime that the evaporator was operating in. And from that, we can make comparisons between the model and the experimental results. A few notes on potential sources of deviation in our results. Contamination in the form of oxidation, corrosion, or any oils can affect our boiling characteristics and increase our surface thermal resistances. Failure to purge any non-condensable air can degrade our condensation performance, can also result in oxidation. And this is likely because our vacuum seal can be degraded due to repeated opening and closing. It took a lot of work to nail down our sealing procedure and a lot of opening and closing on the swage lock. So damaging those threads is definitely a possibility. Additionally, as I discussed, any heat flow losses on the exposed evaporator section and through the G10 base plate can reduce the total input and increase uncertainty in what the actual heat input into the pipe is when we're talking about a model comparison to the experimental results. Additionally, filling inaccuracies result in uncertainty of our working charge mass. So the fill, purge, boil off method is great for creating a simple hermetic seal, but using a balance to track evaporated mass losses in real time is by no means the most accurate method. So there are uncertainties in the working charge mass, and then in turn that creates uncertainty, particularly in the active area for your two-phase heat transfer processes. And then finally, and probably least importantly, but still a source of uncertainty, is the thermal conductivity of printed aluminum. So we did not assess the conductivity itself, and that value, due to it being 3D printed, is typically going to be a lot lower than pure aluminum. To quantify some of these result deviations, we created a heat pipe performance timeline. So you can see for every single data set, 1 through 4, we've plotted the delta T values. And you can see, particularly for the 5-watt case, from data set 1 to data set 4, there's almost a 100% increase in the measured delta T values. It's important to note that this was with very similar charges, and charge sensitivity analysis was performed. So deviation in charge mass was not the source of this. It truly was performance degradation. So the degradation of our heat pipe performance with time definitely indicates some changing characteristics within the pipe. And this also aided to our understanding of the different heat transfer processes that were occurring, because the 15-watt curve you can see is relatively consistent. And to us, that indicates that 15 watts was a sufficient heat flux in order to initiate boiling. But what we were seeing in the 5-watt case, increasing in delta T so drastically, was a further and further delayed onset of boiling, and natural convection continuing to dominate at higher heat fluxes, which resulted in less efficient heat transfer and a higher temperature drop. Overall conclusions are that despite the performance degradation, additively manufactured heat pipes do demonstrate successful operation without significant post-process machining required. Additionally, the Python model matches the experimental results within the target of 25% for 12 of the 15 cases. The 25% target, again, corresponds to the assessed operating heat transfer mode based on both expected boiling behavior and trends in the experimental results. The other 3 out of 15 cases in which the Python prediction falls outside of the target may be explained by experimental uncertainties in the temperature measurement, the working charge mass, and the contamination effects that I discussed previously. It's important to note as well that the model does show a better agreement for early runs. 2 out of those 15 cases were from the very final run that was performed. And as you can see from the timeline that I showed previously, the performance degradation was certainly apparent. And because of that, we do conclude that the Python model is accurate in predicting the overall heat pipe performance. Some future work includes further quantifying our uncertainty analysis by performing more sensitivity studies, looking at air propagation through our measurement instruments, etc. We also want to refine the filling and sealing procedure to reduce that uncertainty in charge mass and also allow for long-term use. So in doing that, we would have a more accurate prediction of the active areas, the amount of pipe surface area that was covered by liquid, and then also we would not have any performance degradation for the loss of our hermetic seal. Additionally, we would want to use a cold plate or a pumped fluid loop for the condenser heat rejection. We opted for a fan for simplicity, and obviously a cold plate or pumped fluid loop is going to add some complexity to design, but it would allow for maintaining a constant condenser heat rejection temperature, which would allow for better comparison between runs because your heat pipe performance is dependent on the temperature of your test. And then also it will eliminate convective loss uncertainty from using a fan. We also want to print a test block of known dimensions for the thermal conductivity to be measured and design an adjustable tilt mount for the heat pipe to be tested at various angles corresponding from reflux mode, which is what we assessed here, all the way to horizontal and potentially even adverse tilt angles. Doing that would just expand our testing capabilities significantly. And then finally, our ultimate goal, as I stated at the beginning, is to print a larger integrated structure with embedded heat pipes for testing. Example of this would be a CubeSat bus panel. We would perform a similar procedure as we did here, comparing the dry bus panel to each of those embedded heat pipes being charged with some working fluid, and we would make assessments about the feasibility of the design. But as a first cut, we can say certainly that the additive manufacturing heat pipes do present an opportunity for reducing the temperature gradient across some of these structures. So it does warrant kind of looking into further and seeing what the application could be to a full-on space vehicle. A few quick acknowledgements from our side of the program would be David Witkin, Vinay Goyal, Mike Benson, and Mike Rosato. But that concludes my presentation. I can take any questions you guys have. Thank you.
All right, thank you. Excellent presentation. Yeah, audience members, encourage everyone to type your questions into the chat and we can read them off here. I wanted to ask one just off the top here. Just with the 3D printing method that you used, did you do anything special to try to get residual powder out of the heat tank?
To my knowledge, no. I think that they just rinsed it out. We thought about putting it in like an ultrasonic cleaner or using a compressed air machine to try to clear it out. But to my knowledge, no, we didn't notice any residual material still left in there after the print.
Okay. All right. Thank you. I see we do have a question in the chat here. Has heat pipe undergone any thermal cycling to see how much effective is actually the sealing? Degradation through the runs is reported. Have you weighed the item to assess if that is due to fluid leaking? There's a couple questions in there.
So let me start with fluid leaking. We have weighed it pre and post fill, and our initial estimates with the first NPT fitting. First off, it was leaking because it was dry at the end. We filled it with 1 gram, and by the end of the test, there was no liquid left. By the end, we did see about a 15% difference in the pre and post mass of the pipe. So there is certainly some leakage occurring. And then what was the first question on top of that? Oh, thermal cycling. We did not perform any thermal cycling on this. That would be something that we should look into for future tests, just seeing if degradation from temperature cycling would be a potential source of error too.